You see it everywhere. AI creating these stunning images, writing poetry, answering ridiculously complex questions. It honestly feels like magic. But what's really going on under the hood? Well, today, we're going to peel back the layers and look at the actual engine that powers it all. And you'll see it's a lot less magic and a whole lot more math than you might think. It's one thing to see the incredible results, right? But how does a machine go from basically knowing nothing to generating a sonnet or spitting out lines of code? How does it actually learn? That's the real mystery we're diving into. Okay, so let's start with something we've all probably done. You give an AI a simple prompt, and a few seconds later, boom, you get a creative, coherent response. The journey from your words to its words is where all the action is, and that's the process we're going to unpack. To understand that journey, we first need to look at the structure where all this so-called thinking takes place. We're going inside what's called the neural network, which, you can basically think of as the AI's brain. So what is a neural network? Well, imagine a massive digital switchboard with millions or even billions of interconnected points. The process of learning is really just about adjusting the settings on countless tiny little dials. Each one influences the final outcome, and the goal is to fine-tune every single one of them until the network consistently gives you the right answer. And that's really the whole game. For every single prompt you give it, like our haiku, the AI needs to find the absolute perfect combination of settings for all of those dials to produce the best possible output. It's a massive, massive tuning job. So how does an AI actually turn all those dials? It needs a language to do it, a mathematical language. And this brings us to the one core calculation that makes literally everything else possible. Believe it or not, this entire revolutionary technology doesn't rely on hundreds of different complex formulas. Nope, it's overwhelmingly powered by one single fundamental mathematical operation. And that operation involves these things: matrices. Now, it looks a little intimidating, but don't worry. A matrix is really just a grid of numbers. Seriously, if you've ever used a spreadsheet, you already get the basic idea. It's just a structured way to organize numbers for doing math. Here's a simple one, just a bunch of numbers in rows and columns. It might not look like much, I know, but these little grids are the fundamental building blocks. They're the language the neural network uses to represent everything and to do its calculations. Okay, so let's get into the core operation itself, matrix multiplication. It sounds complicated, but the process is surprisingly straightforward. You just take a row of numbers from one matrix and a column of numbers from a second one. Then you multiply the numbers that line up, and finally, you just add up all those results. That's it. That is the one simple calculation that powers almost everything we see in AI today. Now, that process seems pretty simple, right? Multiply, then add. But here's the catch. The real challenge isn't the complexity of the math. It's the sheer mind-boggling scale at which it has to be done. So let's go back to that simple process we just walked through. Multiply and add. Now imagine doing that not once, not 1,000 times, but an almost unimaginable number of times, just to tune every single one of those little dials in the neural network. This is the number we're talking about, a quadrillion. That's 1,000 trillion, a 1 with 15 zeros. Training just one large AI model can mean doing that simple matrix operation a quadrillion times. Just let that sink in for a moment. And this isn't an exaggeration. It's a computational task of astronomical proportions. And that right there is why you can't just train a cutting-edge AI model on your laptop. You need something more. See, a standard computer chip, a CPU, is a jack of all trades. It's designed to do a lot of different things pretty well, but it's not a specialist. For a task this repetitive and absolutely massive, you need a specialist, something built to do just one thing, that one simple math operation over and over and over again. And that specialist is the GPU. This need for a specialist has created a kind of hardware arms race, leading to what is basically a dedicated AI math engine, a supercalculator built with one very specific superpower. And at the very heart of that engine are these things called Tensor Cores. These are highly specialized little circuits built right into modern GPUs. They have just one job in life: to perform that matrix multiply and add operation at lightning speed. And this is exactly why they're such a total game changer. Because they're designed for only one job, they have extreme speed. They can also perform thousands of these calculations all at the same time. And all that focus makes them way more energy efficient. They are the piece of hardware that makes the quadrillion calculation problem actually solvable. So let's bring this all together. From a simple prompt to a creative output, we've gone from the AI's brain to the one math problem it needs to solve, and all the way to the specialized hardware that makes it possible. So the entire logic really boils down to this. An AI learns by tuning the millions of dials in its neural network. That tuning process is driven almost entirely by simple matrix math. But, and this is the key, it requires doing that math a quadrillion times. An effort that's only possible because of specialized hardware, like Tensor Cores, designed specifically for that one task. So the crucial takeaway is this. The incredible, seemingly magical abilities of modern AI are not the result of some unknowable, complex consciousness. It's the result of performing very, very simple mathematics on a scale that was, until pretty recently, computationally impossible. And that leaves us with a really fascinating final thought. If everything we're seeing today, all the creativity and all the problem solving, is built on the foundation of what is basically simple arithmetic done at an astronomical scale, what happens next? What becomes possible when the math itself starts to get more complex?